This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Welcome to Software Engineering Radio. My guest is Jun Rao. He's a software engineer and researcher, formerly of LinkedIn, who is embarking on starting a company that is largely based on the Apache Kafka project. He's a researcher and developer who has spent much of his time researching MapReduce, scalable databases, query processing, and other facets of the data warehouse. And for the past 3 years, he's been a committer to the Apache Kafka project, which will be a focus of our discussion. So, Jun Rao, welcome to Software Engineering Radio.
Thanks, Jeff. Thanks for inviting me.
So to get started, let's talk about a couple of definitions. So how would you define streaming and how would you define messaging?
Yeah, that's a good question. So streaming, based on sort of my view of it, historically has been mostly referring to systems or frameworks that provides the capability of processing one or more sequence of infinite events. So those frameworks typically provide things like the ability of plug in customized logic for processing those events. You can do things like filtering, window-based aggregation, or string-based joins. That framework typically also provides things like parallelism. It will parallelize the event for you. You don't have to worry too much about it. And those frameworks typically also cover things like fault tolerance. So if one of the processing unit is down, you don't have to worry about it because the framework can restart the process in some other machines for you. So this is sort of my view of what this stream processing system refers to. So based on that definition, things like Apache Storm and Apache Spark, and there's another system that's has been built at LinkedIn called Apache Samza falls into this category. These are the systems that provides a framework for processing sort of sequence of infinite events. Now, one of the things those systems have to worry about is where do they get the data? That's where the messaging system comes in. So one of the key way for those stream processing system to get data from is from a messaging system or a PubSub system. So if you look at Apache Storm, the most popular way for you to get data is from Apache Kafka, which is a messaging system. And there's the integration with Kafka in other streaming systems like Spark and Samza as well. So that's sort of I view as the difference or the relationship between streaming and the messaging system. So another sort of a analogy, if you want to map that to the Hadoop world, the Hadoop part has two systems, right? One is the MapReduce part, which is really the processing framework of those offline data. And then there's HDFS, which is the storage and the delivery mechanism of those data. And these two systems are coupled together in a loose way to provide this offline computation framework. And you can view sort of this streaming processing system as the equivalent of MapReduce, but more in the real-time world. And the messaging system like Kafka are sort of equivalent or the counterpart of HDFS, but again, it's for the real-time world.
So that's interesting that you kind of describe it as the Kafka and Storm projects is sort of being an unbundling of things that are frequently found together, or in other domains found together. So, and I guess let's talk a little bit more about specifically what Apache Kafka is. The summary that I found is a publish-subscribe messaging system rethought as a distributed commit log. So, what do you think of this definition, and why is it useful to draw an analogy between messaging and a distributed commit log?
Yeah. So yeah, it is true. I think Kafka at a high level, the definition is really sort of messaging or PubSub system. So the line between messaging system and PubSub system is a little bit blurred these days. Traditionally, messaging system has been mostly referring to systems where you sort of do this point-to-point message delivery, right? So message is published from one place and it's delivered to another one. And if you look at the PubSub world, there I think the analogy is the difference is messages can be consumed multiple times, potentially by different consumers. So, but these days I think the line is blurred because a lot of systems can support both. Now, why do we draw the analogy between a messaging system and a commit log? So I think there are two things. One is at the very high level, both messaging systems and a commit log are dealing with sort of a sequence of append-only data. So the access tab pattern is pretty simple. To write the data into those systems, you just keep appending new data into your system. There's typically no updates. You just keep adding new things. The way you read it is also pretty simple. Typically, you just read those data sequentially. Now, because of such simplicity, it comes a lot of benefit. Basically, you can implement this system in a very efficient way in terms of scalability, reliability, and performance. So that's the first sort of analogy. The second thing is, so I came from the database background. So if you look inside a database system, right, most of the databases has a commit log. Now, that commit log is actually the source of truth of all the data you store in a database. Even though it may not be kept forever, but that's actually where the initial data comes in. And from that, you can derive all the other data you have in the database systems, like data you store in a table, data you stored in the index. So this is also true for messaging system. If you think about all the consumers or the downstream applications that gets data from a messaging system in some sense serves as the source of truth for all those downstream systems. So that's sort of the second analogy between a messaging system and a commit log.
Okay, and so how does Kafka compare to more traditional messaging systems like ActiveMQ or RabbitMQ?
Yeah, that's also a good question. That's a question that we got a lot. I would summarize there are two key differences. One, these are the differences where Kafka has a little bit of advantage. So one is Kafka is really designed for high volume data. If you look at traditional messaging systems, those systems typically are only responsible for storing data that's generated in the database. But if you look at Kafka, it's really designed for systems. It's really designed for storing data such as business metrics, service logs, operational metrics. And those data, in terms of volume, is easily 100 times or 1,000 times bigger than the data you store in a database. And it's not something traditional messaging systems are designed for. And Kafka is really designed for those. For example, Kafka designed as a distributed system from ground up. So if the volume of data increases, we can just easily add more machines into the cluster to handle that volume of data. And there are quite a few optimizations in various components where we do batching and compression so that we can handle this volume of data more efficiently.
Okay, so that makes a lot of sense. So it's so kind of looking at the size of the pipe from the ground up that you need.
That's right.
And saying we need something that's just way bigger than something like ActiveMQ or RabbitMQ offers.
That's right. So you can think of it as a big data version of the messaging systems. So that's the first difference. The second difference, which is also important, is traditional messaging systems are really designed for, and only for sort of real-time use cases. But for the Kafka use cases, we not only have the more real-time use cases, but an important consumer or downstream application of Kafka is to feed data into those offline pipeline. So one of the most important ones, of course, is Hadoop. A lot of people are using Kafka to get data into the Hadoop system. So, in that case, what we have is system that you need to handle both the sort of real-time use case as well as the non-real-time or the batch-oriented use cases. A lot of traditional messaging systems, because they really optimize for the real-time use case, they do things like buffering all the messages or unconsumed messages in memory. So now imagine if you have a downstream consumer like Hadoop that's under maintenance for a couple of hours, right? Then you may not be able to buffer all those data in your message broker for that long.
So would you... Oh, sorry, go ahead.
And because of that, for a lot of the offline consumer use cases, a lot of traditional messaging systems, the performance falls way short of Kafka.
So would you describe Kafka as a data warehouse messaging system? Or is that too narrow of a definition?
I think, yeah, you can sort of I think it is a sort of a warehouse of data. You can think of it as warehouse data, but it's really a place where you can collect all types of data and you can feed that into different platforms. One important pipe is to feed that into the sort of warehouse or the offline system, but you can equally use the same system to feed data into a more real-time platform. So it's a sort of a integration point for both the offline and more real-time consumption.
Okay, that's great. So now that we have sort of a framework of an idea for our listeners for what Kafka is, let's talk a bit about the basic vocabulary of Kafka and kind of drill down into how it works. So maybe you could talk about how some of the central components work. So could you maybe talk a bit about topics and producers and consumers and brokers?
Yeah. So at the very high level, Kafka is very similar to traditional messaging systems. It has this three-tier concept. In the middle, we have this broker layer. This is actually where messages are stored and served. And of course, we have the producer tier. These actually are the publishers of the messages. And we have the consumers. These are the system that make subscription of one or more of those feed of data, and the data just get delivered to those consumers. So these are at a very high level, sort of three layers of entities around the Kafka. Now, topics are essentially the unit of the logical unit of defining individual feeds. You can think of each topic corresponds to like a virtual queue. And when you publish messages, of course, you publish a message to a topic. So then your data is added into one of those virtual queues. And when you consume a message, consume data, you typically subscribe to one or more of those topics. So then all those data stored in those corresponding virtual queue or virtual channel will get fed into your system. There is also this low-level concept called partitions, which is associated with topic. Now, each topic physically can have one or more partitions. And the reason we have this partition is really for parallelism. So the more you can think of like a virtual channel physically divided into multiple physical queues or channels, and those sub-queues or sub-channels can be stored independently on different machines, and that's a way of getting more parallelism out of our system.
And when you say parallelism, do you also mean like redundancy or fault tolerance, or is it mostly just to speed things up?
I think it mostly has to do with speeding things up. So logically, different partitions can be sort of consumed independently, and whether you replicate those data or not, right? So the more partitions you have in terms of both the producer and the client, so the more parallel channels you can have. So that is a way of increasing the degree of parallelism. Now, each of the partition can be further replicated, and that is a way that we can use to provide the reliability of the system, but it's not related to what we have in terms of parallelism.
So messaging typically has two models. At least there are two that you could discuss: queuing and PubSub, publish subscribe. And with queuing, you have a pool of consumers that read from a server, and each message goes to only one consumer. So in queuing, maybe you have like a list of tasks that the server needs accomplished just once, and it just has consumers that are receiving each of those tasks. And then in PubSub, the message is broadcast to all consumers. So Kafka has a single consumer abstraction called a consumer group that generalizes both of these. Could you talk a bit about consumer groups and how and why they were conceived?
Yeah, certainly. I think consumer group, yeah, it's pretty interesting. So as you said, it actually covers sort of both use patterns. In one case, what you can have is you can have just a single consumer group, and in that group, you can have multiple consumers. And what they do is they sort of jointly consume one or more of the topics. So for example, so you have like two consumers in the same consumer group, then a topics data will be hopefully evenly divided half and half between these two consumers. So that's sort of a way of increase the degree of parallelism in the consumer. In a lot of use cases where the logic in the consumer can be a little bit CPU intensive or time consuming. Of course, if you have more degree of parallelism, then you can use more CPU power and other resources to speed up the processing of the data. So that's one use case. Another use case, of course, is you can have multiple consumer groups on the same topic. And this is sort of the multi-subscription model. And in that case, each consumer group will get a complete feed of all the data in the topic. So this is actually intended for, there are just lots of applications. They want to consume the same data, but they just want to process them in a slightly different way or for different applications. And this multi-subscription model is a very powerful way for those applications to sort of consume those data independent of each other. And you can actually have, even for multiple consumer groups, within each consumer group, you can still have those multiple consumers. So you sort of can combine the benefit of the multi-subscription and the degree of parallelism within each instance of the consumption. So that's how we sort of combine both concepts into this consumer group.
And what other facets about the relationship between producers and consumers are unique to Kafka?
Yeah, in terms of, yeah, I think actually a good question. I think one of the things, if you compare Kafka with traditional messaging systems, one of the things we don't have is some of the more traditional messaging APIs, such as like the GMS. GMS has like a rich set of features in terms of like order delivery, priority, this kind of stuff. That we don't have in Kafka. As I said earlier, Kafka is really designed for high volume of data and for dealing data in an efficient way. So, but we don't have a lot of features that's existing in traditional messaging systems.
And so does this lead to some trade-offs where there are sort of like explicit use cases where Kafka just doesn't really make sense as your messaging system of choice?
Right. So it depends on your application. On the one hand, Kafka does support some basic features that a lot of applications want to have, such as the guaranteed delivery. There's like a producer-side API allows you to configure when you can get an acknowledgement when you publish a message. Different ways of acknowledging gives you different guarantees on durability. That actually a lot of the users are using for the applications. Now, what we don't have is some other things like the priorities, order to deliver, various out of order delivering. So if you have requirements of that, then either you have to implement in your application, or you just have to use some other messaging systems that gives you these capabilities.
So talking more broadly or historically, there have been a lot of platforms over the last few years. We've mentioned some of them so far. So what do you think are the factors that are driving the emergence of this important technology, and sort of like where you're kind of at the forefront of developing this kind of stuff. So what do you see changing in the future, and how do you see what evolution of this domain do you see?
Yeah, that's also an interesting question. So I see there are two important factors that have changed. One is sort of the volume or the type of data that people are collecting. Historically, most of the data people that are of interest are just database data. But in the last 10 or 15 years, people started collecting those what we call big data. So what are those data? These are data such as business metrics. These are like the page views, impressions, clicks, search keywords people typed in. This also include operational metrics, or the GMX, IO stats, CPU stats. This also includes all the service logs, like log4j logs, syslogs, or maybe some other service calls. Now, in terms of volume of data, these data is easily 2 to 3 orders of magnitude bigger than the data stored in traditional database systems. In terms of value, these data provide a lot of insights that's actually valuable for lots of downstream applications. So that's trend number one. The second thing, which is also related, is which is the question: why people are only starting to collect this data sort of more recently instead of like 15 or 20 years ago. This actually has to do with another trend, which is the emergence of a lot of scalable, specialized vertical systems. So if you like the Hadoop, Hadoop is a specialized, scalable system for doing offline processing. Traditional, a lot of those things, the only place you can do this kind of stuff is in Oracle or Teradata, which is expensive. But what Hadoop did is very special. They basically take one aspect of it, which is offline processing of the system, and made it more scalable on commodity hardware. As a result, they can provide an offline processing solution in a more economical way. And because of that, people actually can now afford to store this large volume of data if they want to do offline processing in Hadoop. They don't have to buy those expensive Oracle or Teradata instances. So this kind of trend is not only happening in the offline world, but it's actually starting to happening in many other vertical specialized domains. So if you look at a search, there is the Elasticsearch that's doing the sort of scalable version on commodity hardware in the search domain. And if you looked at key value stores, right, there are lots of systems that provides the capability of storing and retrieving like point data in a scalable and economical way on commodity hardware. And if you look at, there are lots of like graph engines. Those are like systems that can do graph processing, but again, on sort of commodity hardware in an economical way. There are lots of like a streaming system that also are designed to be designed on commodity hardware that you can scale in a more economical way.
And do you think that the big cost of storing this kind of data is sort of trending towards the fact that you have to maintain it, as opposed to whether or not you can afford to store it?
Yeah, I think both aspects are important. The first, of course, is upfront cost, right? How much does it cost for you to acquire the software and the corresponding hardware? That, of course, if your software is like free, like open source, and your hardware is can run or only depend on commodity hardware, then it's going to be a lot cheaper than you have to pay a premium on proprietary software, and you have to pay a high premium on expensive storage boxes instead of just commodity boxes with large local SATA drives. So that's the first aspect of it. The second thing, of course, once you have your system in place, you have to operate that, right? So there, of course, the more instances or the larger the cluster you have, the potentially the more overhead of monitoring of operationalizing it. So there, I think that a lot of tooling would definitely help. If you have a lot of tooling and monitoring in place, then it doesn't really matter whether you are monitoring a cluster of 10 nodes or a cluster of like 100 nodes, because a lot of things can just be integrated together with the right alert and monitoring set in place. So that will certainly help to drive down the operational cost of those systems.
Okay, so let's get back to talking a little more about Kafka specifically. So maybe you could describe I know you've touched on some more abstract examples of Kafka, but maybe you could talk about a more specific use case where somebody would want to deploy Kafka, and sort of describe how they would go about deploying it and connecting the different components.
Right. So at a high level, this sort of goes back to the changes of industry trend I mentioned a little bit earlier. So because of those existence or the emergence of those very specialized sort of scalable systems, so a lot of those systems, if you look at those, they need to be fed with the same type of data. For example, if you have a collection of log data, right? Of course, you want to feed that data into Hadoop for offline processing. But equally important, you probably want to feed that data into your search system so that you can search any of the log occurrence quickly. That's a lot of the business what Splunk does, right? And equally, if you have, for example, a stream of like operational data, of course, you want to feed that into your offline system, but you probably want to feed that into some of your real-time monitoring system so they can monitor and graph those data. So, so the question is, where do all those independent systems get their data from? So you sort of need like a integration point that where all those systems can get its data from. Now, a lot of those systems are actually, unlike Hadoop, they are actually more real-time. So you can't really just integrate that in your warehouse or offline system, because in terms of latency, these systems may not be good enough to provide data feed to some of the more real-time applications or frameworks, such as real-time search and graphing. So Kafka sort of fills in that role, because it's a system actually designed for collecting and storing high volume of data. It actually can provide feed to any number of downstream applications, and those applications can be sort of more real time, but those systems can also be offline. So you can sort of as a like integration hub for all this big data. Now, in terms of Kafka adoption, what we have seen, of course, is people are picking up sort of various pieces. One common use case, of course, is people are using Kafka as this ingestion pipeline to get data into Hadoop. But at the same time, they also have application, one or more of the application for real-time use case. Be it a specialized real-time application, or some of the streaming processing framework they are adopting, or some of the real-time search system they are adopting. So because of those need of more than one application of the same data, so Kafka sort of is very important for them to get those various pipelines working. So that's one of the common pattern we see Kafka gets adopted.
Have there been any implementations you've seen that have like really surprised you and maybe ended up maybe even changing the direction of the project, or sort of introduced a reason for adding some new features you wouldn't have predicted?
Well, I think so far, there are lots of features that we know are required as Kafka gets more and more adopted. Things like security, which is important. And in that domain, we don't see too many like surprises in terms like future feature requirements. We are sort of surprised occasionally just the way people are using the system. There are lots of things that we sort of didn't plan to have people use it in that way, but people use it in any way. Sometimes is not really sort of ideal use case, and sometimes we're surprised that Kafka actually works when people use it that way. For example, one of the things we are surprised that there are at least one use case that are using Kafka sort of as a message delivering mechanism, and the way they send messages, each message is sort of gigantic. Those are each message can be a gigabyte. Of course, you can configure Kafka to do things like that, but it's certainly not something that we really designed it for. But we're just surprised that people are using it and then sort of worked in this limited context. There are other use cases like people are sort of trying to use Kafka more like a key value store, where they just sort of randomly consume messages from different places. That also sort of can work, but it's not really something that Kafka is really designed for. So that I would say, architecture-wise, if you have a use case like that, probably a key value store is more appropriate for those use cases.
Yeah, that's really surprising. That sounds like the type of thing where it's you have somebody with a hammer and everything looks like a nail.
That's right.
So in the 2011 paper about Kafka, there is a distinction that is made between application data and log data. And so this distinction has become less clear over time. Do you think Kafka is still viewed as a log record messaging tool, is it less acceptable now compared to 3 years ago if some of the log records are dropped?
Yeah. So one of the things we have seen, of course, the way Kafka get adopted typically starts from people putting in log data. And that's actually what Kafka is really designed for, and it's a powerful way to store and serve this kind of large volume of data. And arguably, maybe for log data, you can argue maybe it's okay to lose a few messages from time to time. But over time, of course, what people want to have is once you have a pipeline that can serve high volume of data, right? Then people would think, oh, why can't we move all the data, including some of the more application or maybe database data, into this pipeline? So then for those data, of course, those are more important data than log data. Some of the durability and reliability guarantees will be stronger. So that's one aspect of it. Another thing is when you publish data to Kafka, one of the things you can do is sort of do this semantic partitioning instead of just a random distribution. So for some applications, maybe what you want to have is, for example, all the messages associated with like a particular like user ID, right? You want that to be consumed by one consumer. So the most convenient way you can do that is to partition the messages by this partitioning key, which can be the user ID. Then you guarantee all the messages belonging to the same user ID will show up in one partition, and as a result, will be consumed by only one consumer. Now, to do things like that, it actually requires each of the partition to be made highly reliable and available, right? Because now, if you imagine if one of the partition is offline, right? Now you have a message semantically based on the key, it has to go to that partition. If that partition is not available, what would you do? You probably have to drop it, or if you map it to a different partition, then essentially that changed the meaning of your semantics, which may not be ideal either. So that's why for those cases, reliability and durability is actually equally important when you have even just log data. So for that, in the last couple of years, we actually have spent a significant amount of time on Kafka just to add the reliability and durability support in Kafka. So what we did is, for each partition of Kafka, you can have multiple replicas. And when you publish a message will be redundantly stored on multiple replicas, typically in different brokers. Then, if any of the broker fails, there's a logic in Kafka that allows the system to continuously function when there are individual broker failures. So from the end user's perspective, both the producer and consumer, it's as if nothing has happened, because the underlying systems will route the connection from the client to the alive brokers that has the same copy of the data. So that's actually one of the important things we added in Kafka.
Is this performed by Zookeeper?
Yes, I think the way this works is we use Zookeeper for storing some important state information per partition. In terms of the amount of data, it's not a lot. There's only like maybe a few bytes of information that we need to store per topic partition. And what we store there are critical information as who is the leader of a partition. I think in the world of replication, typically you will have multiple replicas associated with a partition. One of them is designated as the leader, which takes all the writes, and the other replicas are followers, which just takes data from the leader. So when the leader fails, of course, you need to be able to quickly elect a new leader, and then continue serving data from the new leader. So we rely on Zookeeper to store information like who is the current leader of a partition, and equally important, who are the correct or possible candidates for becoming a new leader had the original leader fails.
Right, and what's interesting is it seems like the ability to just I guess offload I'm not sure how much energy is offloaded onto Zookeeper, but it sounds like a significant amount, and it makes me think back to the what you said earlier on in the conversation about how the Kafka is analogous to if you look at Kafka and Storm, it's analogous to unbundled components of Hadoop, and it makes me think it's interesting that you have Zookeeper that's essentially just like a Lego block that you just is now a central component of Kafka, and so all that makes me think about what are can you conceive of future type of components, maybe open source or not, that would be built on top of Kafka?
Yeah, so that is a good point. I think for now, Kafka, you can think of it as a place where a feed of data is provided, and given the sort of reliability and durability guarantees we have, it is possible for people to store like the source of truth data in Kafka. Now, in some sense, you can view it as sort of the commit log in the database world. Now, from the source of truth of data, there are lots of systems that you can potentially build on top of it to get a feed of data and then sort of convert data into a format that's easier for processing for a particular vertical domain. So there has been systems, for example, in the key value store domain, where it relies upon sort of a distributed commit log as the centerpiece for storing and recovering data. Now, we haven't tried this in Kafka, but it is possible for someone to take Kafka and then use it as a sort of a commit log as a source of truth and build other surrounding systems like maybe another key value store or other storage systems around it.
Okay, interesting. So to go back to a little bit more about the PubSub model, because I see that as fairly important to this discussion, and I'd like to just maybe, even if this involves rehashing some stuff that has already been discussed, I think it'd be worthwhile. So coming back to the topic of PubSub, so each topic is analogous to a publish channel in the PubSub model, and as I understand, each of these topics has one or more partitions, which is a block of memory that is allocated to it where new messages are appended. And at any given time, you have each subscriber to a topic that has consumed up to some point on that partition. Would you describe that as? Do you think that's an accurate description of how partitions and channels work?
Yeah, that's actually it's not 100% accurate. Actually, one of the things what we do in Kafka is remember earlier, I think Kafka is really designed to optimize for both the sort of real-time consumption as well as the offline consumption. So one of the things that requires us to think about is in terms of buffering messages. So if you buffer like all the unconsumed messages in memory, of course, that just limits how offline applications you can support, right? Because memory is limited, you can't essentially buffer everything if a consumer is gone for a long time. So what we do in the broker is we don't actually allocate a lot of heap space for storing messages. So every time we get a message or a set of messages from the producer, we simply just append it to the corresponding file channel on the local disk. Of course, we don't flush data immediately for better performance. We sort of flush data in those file channel to disk only periodically. But we don't really keep a copy in the JVM heap space. We actually immediately just put the data into the file system. But most of the time, file system has its own page cache, so chances are those data are still in memory, but just in the page cache managed by the file system for us. It's just that we don't have to manage that in the JVM heap space, which is a lot better for GC tuning and other things. Now, in terms of consumer, we do the same thing. We do similar things. We use the sort of Unix standfile API to send data from a local file channel to a remote socket directly. Again, from the consumer's perspective, we don't have to take any heap space by first copying the data from the file channel into an application space, then copying the data from the application space into the remote socket. We sort of rely on the operating system to do this for us more efficiently. So because of that, Kafka, at least the broker, is actually very efficient in terms of JVM heap memory usage. Typically, we don't require a lot of heap space, and we only need sort of a limited kind of tuning for GC management, because we don't have a lot of permanent space that's taken by the JVM heap. A lot of the memory consumption are like transient per request.
Okay, that makes sense. So, and let's talk about another aspect of I guess distributed systems in general and how it pertains to Kafka specifically. So, I'd like to talk about durability. So, are messages recoverable across restarts and failures?
Right. So so there are different like failures. On the broker side, as I mentioned earlier, we added this replication support. So within a single cluster, messages can be redundantly stored on multiple brokers. So now, if one
and real quick, would you say a broker is synonymous with a topic partition?
A broker is actually, think of like just like a server or a node where multiple partitions data can be stored upon.
Okay.
Okay. So it's sort of like a engine where we store those messages. And in a cluster, you can have multiple of those storage engines, but the topic partitions or the replicas, they are sort of spread around into those storage engines. And each storage engine or broker typically stores multiple partitions.
Got it. Partitions from different topics.
That's right. Of course, each partition typically corresponds to a local file directory, and sort of takes its has its own set of files from other topics. So there's going to be isolation at the disk level. Now, in terms of reliability, if you configure a topic to have multiple replicas, then the broker on the broker side, it can tolerate broker failures. The common failure in the Kafka class, of course, is those we call soft failure. The brokers actually are healthy. You just want to deploy new code or make new config changes. Because of that, you have to bring one or maybe each of the broker in the cluster down and then restart them. So that's actually maybe 80% or maybe 90% of the failure cases in a Kafka cluster. So with replication, of course, we can handle this kind of failure very effectively. We have the logic to automatically just fail over the leader of each of the partition to another replica, and all the clients will just behave seamlessly in these cases.
So it sounds like it's not really within the spec of Kafka to back up messages to a durable store. Is that accurate?
Yeah, actually, that's sort of orthogonal. Yeah, so this, the replication really deals with for a message, where we store those and how we make sure we keep them in sync among those different replicas. Then a second issue, which is sort of what you are pointing out, is how long do we keep a message around in a Kafka cluster? So this is also a little bit unique with Kafka, is the retention of a message is actually not driven by consumption, as in typical messaging systems, in the sense that a message is not like deleted from the Kafka once all the consumers have finished consuming of this message. Rather, messages are retained based on a retention policy. And that policy can be driven by time. You can, for example, keep the messages for like 7 days or maybe a month, whatever you feel that you need those for. And it, of course, can also be retained based on sizes. So maybe you want to keep let's say a terabytes of data, right, around. So the one of the important aspects with this kind of retention is actually a pretty useful feature. What it gives you is what we call the rewindability from the consumers, in the sense that a consumer, after finished consuming a message, if it wants to, it actually can consume the message again, as long as that message is still within the retention window. There are some use cases of this. I think one important use case is this can deal with like an application error or a logic error very effectively. So imagine like you have a application that consumes a feed of data from Kafka and do things like standardization, right? You standardize each of the data and into some canonical format. But let's say at some point you push some new software and you had like a serious bug. And you realize that only a bit later, maybe an hour into it, you say, oh, or the data that processed in the last hour is not usable because of the bug. So now what you do? So with this sort of a retention policy, what you can do is you can actually rewind the consumption of your messages from like an hour or maybe 2 hours ago, the point where the buggy code is introduced. As long as those messages are still retained there, you can actually just reapply the new logic, which presumably have fixed that bug, and just run through those same data again. Then you can recover you can correct all the mistakes you have made on the previous computation logic.
That sounds like a super important feature.
That's right. So that's something that not all the traditional messaging provide, and
right,
we
the ability to go back in time.
That's right, the ability to reconsume some of the messages over time, and fixing application logic is one of the important use cases for this.
Cool. So one of the words that we hear a lot on this podcast is the word microservice. So what does the word microservice mean to you, and is that something that's appropriate to this conversation as as what Kafka is and what it provides?
Yeah, so actually, I'm not 100% sure what those microservice means. What do you what's your interpretation of those microservices?
Sure. So what I would think of a microservice as is something that is a service that can be, or to put it in this context, a service that could have a call made to it over a message broker. Just a small service that if X needs to get done, you could make a call to it over whatever message broker you have. The service gets performed, and the advantage to these sorts of services is that as you can modularize them, and it becomes easier to scale more instances of them. Yeah, but I as I understand about the word microservices, that it means different things to different people. So that's part of why I brought it up. But if you're not even really familiar with it or comfortable discussing with it, that's totally fine.
Yeah, I'm not 100, but I think sounds like is that sort of more an ad hoc use of the message broker, where you want to like start up some like services just for like a short window of time, and then you want to do some processing of the message, and then after that you can just stop the service.
Yeah, that's exactly what I'm saying, and I'm just kind of wondering if Kafka serves that purpose ever.
Yeah, actually, one of the things actually, this actually has to do with the multi-subscription model that Kafka provides. Because one of the powerful things that we see people is enabled with Kafka is the ability to do debugging on Kafka. So this can happen in the production environment, but more often it happens in the sort of testing or the the pre-production environment, where of course you have all the applications that's written up to consume like a feed of data, but sometimes it's actually if the application doesn't work as expected, right? How do you know what went wrong? So the ability of doing multi-subscription allows you just to easily tap into like a topic, use from a command line tool or on a console where you can actually see what the data are, and then based on that, potentially we'll have a better idea whether it's a problem is you don't get the right data or there's something else in the application.
Okay.
So that's sort of like a special case of the maybe microservice that you are referring to.
Sure, sounds good. So in terms of I'd like to talk a little bit more about the development of Kafka. Why was the Scala the language of choice? Like, and more specifically, did you consider Erlang?
Right. I think, when we started this, I think Jay Kras was the first developer of Kafka. Around that point, he was Scala is getting a little bit popular, and he was thinking of like learning Scala. So that's why I thought he picked Scala. It's sort of a way of just to try it out and then see how it works. And from developers' perspective, it's always like interesting and exciting to try some new, like promising programming languages. Now, for Scala, I think what we benefited a lot from Scala is mainly the sort of conciseness of the syntax. We use a lot of the functional support on the collections, which allows writing code of iterating collections very convenient. And because of that, if you look at the Kafka code base, it's actually significantly compared with some of the similar system but written in Java, and we benefit a lot of just from the Scala concise syntax. But one of the things we found that's a little bit difficult with Scala, this actually mostly has to do with the clients, which is because Scala is sort of emerging technology, is not as mature as like Java in terms of like preserving binary compatibility. Just because it's early, in some of the early releases, Scala really have to break the binary compatibility. So some of the bytecode generated in early version of Scala won't be able to run on a new version of Scala, right? So this actually creates some problem for upgrading our clients, because a lot of our clients, maybe they are, of course, using Kafka. Because of that, they have a Scala dependency, but they may use some other components which could also be Scala dependent. Maybe we're dragging a different version of Scala. Now, if the Scala version is not compatible, then it just makes the upgrading of those clients very painful. So that's sort of one of the things that we find is a bit hard with Scala. So we are trying to address this issue by sort of rewriting the client components just in pure Java. So hopefully this will still allow us to get most of the benefit from using the concise syntax in Scala, but at the same time makes the client upgrade a little bit easier going forward.
That's great. So this has been a great discussion of Kafka. Where can listeners go to learn more about Kafka, or maybe even your work on the project?
Yeah, I think the best place to do that, of course, is just go to our website. So if you search Kafka in our in Google, I think Kafka probably is Apache Kafka is probably the first or the second link. So there, it has some documentation that describes what Kafka is and how Kafka is designed for, and some of the examples of how to use our APIs. And you can download the code, and there's a quick start that you can follow. Just try it out. And from that web page, we also have like a link to our Jira system in Apache. If you are interested in contributing, There, you can just search for some of the newbie labels in the Jira system that probably will give you some like a low-hanging fruit that you can give it a try. And we also have like a wiki that describes some of the future release plans and future features. So those are like a more substantial development work that's required. So if you are like a more experienced contributor to Kafka, some of the future projects may be of interest to you. Right now, some of the new things that are coming out of Kafka land, one is we are in the process of rewriting some of those consumer APIs, as I mentioned, to reduce, to remove the Scala dependency and to just make the API more feature complete and better performing. Another thing that's coming up soon is the security support in Kafka. This includes, probably authentication and maybe sending some of the data in an encrypted way. We also have thoughts on how to sort of protect Kafka in a multi-tenant environment. So hopefully different users don't affect each other, especially if one of the application had a bug and becomes like a runaway user. So we have some thoughts on how to use a quota system to prevent things like that from happening. So all those information can be found on our Apache website, and we also have like an Apache mailing list for both the user and developer. And if you're interested, you can just subscribe to those mailing lists and get a feed of what's happening in the Kafka world.
That's great. All right, well, Jun Rao, thank you so much for coming on Software Engineering Radio. It's been a pleasure.
Yeah, thanks a lot, Jeff.
Okay, all right, you have a great day.
You too.
All right,
Bye-bye.
thanks, Jun.
Okay.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /dot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.